All right, in the previous lesson or video, we talked about describing the strength of these relationships. I think we said this was very strong and this was, nonlinear, but the strength was very strong. And then this was moderately strong or maybe even moderately weak. I think I said moderately strong. But wouldn't it be nice to have a way to quantify the strength? Well, of course we do. In statistics, that's called the correlation. Um, um, the correlation, called R, is a statistical measure. Just like the mean is a statistical measure and the standard deviation is a statistical measure, they just measure different things. This measures center, this measures spread of a unit, one variable, whereas this R value is going to measure the strength and direction of the linear relationship between two quantitative variables. So R is a correlation, sometimes called the correlation coefficient, and that's what it measures. So before we get into the actual formula, let's just take a look at some examples and you can kind of see what R values, what R takes on and what it looks like, I guess. So here's a relationship where we have almost random scatter. I will say that if the R value is really equal to 0, there would be absolutely no pattern. Like this doesn't look, this would probably have like a negative R value. But if I were to put maybe a couple points here, like perfect random scatter, that would be an R value of 0. Here we have a negative relationship, but it's still really a lot of scatter. So an R value of negative 0.3. Here we have a positive relationship, but a little bit less scatter, positive 0.5. Now we're getting into the moderately strong negative, so negative 0.7, strong positive 0.9, very strong negative 0.99. So it looks like the R value is changing between negative 1 and positive 1. If it's close to 0, it's a very weak. If it's close to 1 or negative 1, it's very strong. And then if it's a positive relationship, it's a positive R. And if it's a negative relationship, it's a negative R. Exam tip. If asked to interpret the correlation or interpret R, you simply describe the scatter plot. That's using your DUFs. Sometimes kids will see, R value is 0.9 and they want to interpret the 0.9 like 0.9 units of something. It's not. Just basically describe the linear relationship with strength and direction. That's how you interpret R. So here's the formula. If you want to get into the specifics of the formula or how it works, I would encourage you to watch the optional video. I didn't go over it in class, and I'm not going to go over it here. But basically, these are the z-scores of your x variable, of the x variable of a data point, and then this is a corresponding z-score of the y variable of that same data point. If you take the product of those and then add them up for every single data point and divide by n minus 1, you get the R value. I would encourage you to watch the next video if you're interested in how or why that works. But let's just take a look at a couple of examples. These are some applets that are linked in the description of the video, and you can play around it if you want. I'm having a hard time here. There we go. Sorry. So this one here, we just guessed the correlation. There's a sample of data points. We try to guess it. So it's pretty weak, but it's negative. It's actually these points up here that are actually going to increase that R value a little bit. So normally I would have said like negative, maybe like 0.1 or 0.2, but I think this guy up here is going to kick that up to like maybe a 0.3, 0.4, negative 0.5. So even more than I thought. This is pretty strong, moderately strong, negative. So maybe negative 0.7, negative 0.8. This is pretty weak, but I can see a little bit of a positive trend because of these couple points here. I'd maybe say 0.2, positive 0.2. Ooh, yay me. Pretty random scatter. I'm going to say I don't even know if it's really positive or negative. I'm going to guess a little bit negative, but 0.1, negative 0.1. So you can play around with this, and this is stronger, positive 0.8. And if you wanted to, you could even increase the data set size. Like instead of doing 25 points, you could do like 300 points. Positive 8. Pretty random. It is definitely negative. Again, because of these low points here, that's actually going to increase the R value. And if you want to know why those low values, the bottom right values, increase the R value, watch the next video. I'm going to say negative 0.6, 0.5. If I go through this, I can try to get a really strong relationship. There's a pretty strong positive 0.95, 0.9. And we could try to get one that has perfect random scatter, where you really can't even tell if it's got a slight positive trend, maybe 0.2, 0.04. That's pretty good random scatter. So play around with that and get a sense of what the R values look like for different graphs. And applet number 2 here. I'm going to fire up my calculator so I can use that here in a little bit also. Go to statistical applets, correlation and regression. Now I like this one. This one you can kind of add points and it'll give you the R value as you keep adding points dynamically. So you got to put in 2 points before you can get a line. But if you put in 2 points, they have a perfect R value of -1. Basically, if you get 3 points that are exactly on a line, that's going to have a -0.1 or a positive 0.1. Now, if I add another point, unless I can get that point exactly on that same line, it's going to lower it. You know, if you can get points really close to a line, you get a really small, or an R value really close to -1. Same with the positive. If I keep them really tight in there, 0.998, very, very high R value. Okay. So what I wanted to illustrate was, if I have a relationship like this, you know, it's got a certain R value. I guess it's positive 0.88 or 89. If I add a point somewhere in here, let's say I add a point here. Common question in AP courses is, how does that change the R value? Well, you can kind of think about, is this adding to the strength or weakening the strength? And because this point is kind of further outside than the average of all the other points, I think it would probably increase it. Or excuse me, it'll probably decrease the strength. Therefore, it will lower the R value. That's going to be my guess. I'm going to put the point here. Ready? So it lowered it just a little bit. Whereas if I were to add a point that's kind of close to the line, it'll probably increase it. Maybe kick it back up to that 0.88. Okay. So sometimes we have to try to predict how it's going to change. One thing that's a little surprising is if I add this point right in the center of the data points, like in the center of the X's and the Y's, it's really not going to change it much at all. 0.836 didn't even change it at all. And if you want to know why that is, again, watch that next video. Whereas if I add a point out here with a bigger X and a bigger Y, it's probably going to tighten it up a little bit. Okay. If I add a point here, it's going to really lower it quite a bit. Not a lot, but a little bit. Okay. Also, if I have some R values here like this, as you can see, there's a linear pattern, 0.66 R value. What if I add a kind of an outlier point? Now, it's not an outlier in terms of the line of best fit. So I'm adding a point kind of in the same pattern, but if it's really got a high Y value and a high X value, then how will that change it? And this one you might surprise you a little bit. You might say it's going to strengthen it a little bit. But watch it go from 6.5 or 6.6 to 0.94. So it just took a relationship that was moderately strong, moderately weak maybe even, and it made it into an R value of what would look like a really, really strong relationship. A point that's far outside the data set in terms of X and Y values, it has a very large influence on the R value. In fact, I could give you something that has practically a -1 R value, like a really very strong negative relationship. And if I put a point out here, it's going to change it from almost -1 to almost +1. So the correlation is very strongly influenced by outliers and points that deviate from the pattern. Okay, so be careful about that. All right, let me open up a file here. I'm gonna look at that sprint and sprint and jump logs that we were looking at in the previous example. All right, so let's go through a couple key properties of the correlation. Put a little star by these, I guess. Properties of the correlation: R is always between -1 and +1 inclusive. We talked about that. If R is negative, then the linear association is negative. If R is positive, then it's positive. R measures the strength of the linear relationship only. Let's go back to this point one right here. If I were to ask you what is the R value of this relation, excuse me, not the R value, but if I asked you for the strength of this relationship, you should say it's a very strong nonlinear relationship. But look how the R value is practically 0. So, you know, a strong relationship have an R value of like 0.9 or 0.99. But if it's not linear, then this R value isn't a measure of the strength of a nonlinear relationship. So we don't use the R value if we have a nonlinear relationship. If R is 1 or -1, then it's a perfect linear relationship. If R is close to 1 or -1, then that means you have a strong linear relationship. And if R is close to 0, then it's weaker. If you switch the explanatory and response variables, the R value will not change. So let's explore that a little bit. Well, first of all, the reason that it doesn't change is because you use z-scores in the formula. So you know that, well, or actually I should say because multiplication is, oh gosh, I forget what the commutative or associative, commutative, right? Multiplication is commutative. So it doesn't really matter if you take the z-scores of your y or the z, whatever. It doesn't matter what the x and y variables are. Let me go show you guys how to find the R value on the calculator. There's a couple ways to do it, but the way I like is from the graph. After all, you should never even think about finding the R value unless you know the relationship is linear. So I'm going to put sprint on the x and jump on the y. It looks linear, therefore it makes sense to calculate the R value. So what I like to do is I like to just run the regression line. Menu, analyze, regression, linear. Now it doesn't show it to you when you run the line here, but as we've talked about before, when the calculator does statistical calculations, it stores a bunch of stuff into the document. So we're going to go to our vars key to see what variables are stored in there. You can see we got a bunch of stuff stored in here. We want the stat R variable. That is the correlation. A little cumbersome, but if you want to know what the correlation is, run the regression model and -0.84. So I guess what I wanted to illustrate to you was if I do a new graph and if I put jump on the x and sprint on the y, if I switch around my variables, run the regression model again, I get a different equation, but if you look at that R value, you're going to see that it's the exact same thing. So it doesn't matter what the x and y are. Also, if you change the units of either x or y, the R value will not change. So if I look at this graph and I change these inches on the x-axis to meters or centimeters, it wouldn't change the R value. If I change the sprint times from seconds to days or hours or years, it wouldn't matter. And again, I think the easiest way to see why that is to see that this formula uses z-scores. And you know that when you change units on a system, it doesn't change the z-scores of the system, so of the data set, so it doesn't change the R value. And lastly, R has no units. Again, z-scores, right? Z-scores are unitless ratios, therefore their products are unitless ratios, therefore the sums of their products are unitless ratios, so R value really doesn't have any units at all. Okay, all right. I think this is the example I start the next video with, so check out that next video if you want to see why the R value is the way it is, or why the formula works the way it works. Thank you.